Okay, so welcome to DIYguru. Okay, today we are going to do the powertrain modeling and we will see the drive cycle performance of that powertrain model by applying different driving cycle. Okay, so we will run that powertrain for a different scenario or for a different driving cycle. Okay, so in that powertrain modeling, we are going to simulate the model like this with the motor controller, motor, and as well as the vehicle parameters. Okay, so today in this session, we are going to cover that Tata Nexon EV Matlab model. Okay, so we will design that Tata Nexon electric vehicle powertrain on Matlab, and we will see the behavior of that powertrain with respect to the different driving cycle. Okay, so and before doing that, I will suggest, so if you just go through the specification of the Tata Nexon, so that specification you can take from the Google itself or directly from the site. So you can visit to the Tata Nexon EV site and you just collect the data from there and take out all the data, whatever the data is required to calculate the parameters such as drag coefficient, rolling resistance, and the hill climbing resistance. So these data is required to simulate the EV powertrain. Okay, because when you will give all the specification of that electric vehicle, then only you will get the proper output. Okay, so the thing is, before doing the simulation, collect the data and calculate the required things, like what will be the total mass of the vehicle, what will be the curb mass of that vehicle, okay, and what will be the frontal area, what will be the radius of tire. These things you have to calculate before that. Okay, so if you are having the data before, just simulate the model and enter all the data, whatever you have calculated for any of the vehicle. Okay, and when you will enter all the data, after that you can directly, see the behavior of that powertrain. Okay, so this is very important that you should have the data with you. Okay, so then only you can decide that what will be your battery pack size, okay, and what will be the motor torque and the motor power, okay, and means how your SOC is changing, means what will be the maximum SOC, nominal voltage of the battery, okay, you required for that particular vehicle mass or a particular range. Okay, so these things you need to be specific. Okay, that means you should know the range of that vehicle, okay, and the top speed of the vehicle, acceleration of that vehicle, okay, and the tire radius. These things are very important while simulating any of the powertrain on MATLAB. So you just first go through that specification, calculate the required parameters, and then come to the simulation. Do the simulation, enter your details or the parameters you have calculated, and you will get to know that what is the performance of that specific vehicle. Okay, so now I will tell you that how to simulate the model. Okay, because I have already calculated some of the data which is required for this modeling. Okay, and in between I can tell you that how to calculate these things. Okay, so that you can follow to calculate the data, and that will be very helpful. And in this model, actually, you can take any one of the driving cycle to see the behavior. But in this model, we are doing, this performance analysis with respect to three cycles. Okay, we can say that the three different cycle we will use to see the performance of that electric vehicle, that powertrain, which is a Tata Nexon electric vehicle. Okay, so that performance will give you the comparative study, or it will give you a comparison between if we are driving in the Indian driving cycle or we are driving in a different scenario, that what will be the SOC level, what will be the voltage level, and what will be the current level. These things we can compare. So that will be a very helpful to understand the vehicle performance if you are having a different driving cycle. So basically the driving cycle means that the driving pattern or the driving situation of a particular region over the time, means how your vehicle is going to show the characteristic velocity characteristic with respect to the time and the geographical regions. Okay, so that is we call as a driving scenario, driving pattern of that vehicle for a particular segment. So that we will use. Okay, now I will show you first manual so that you will have some idea that how to do that. Okay, so what are the objectives of this powertrain modeling? So we will create one MATLAB model of an electric car, which is in this case we are taking Tata Nexon EV. Okay, and with the uses of this battery and the DC motor. Okay, so we can analyze the SOC of the battery in comparison of different velocity, or we can say that with comparison to the reference velocity. See, if you are using any of the drive cycle, that is your reference velocity. Okay, so if after the simulation whatever the velocity you will get, that velocity should match the reference velocity or should match the driving cycle accurately, then only you can say that your model is correct and accurate. Okay, you will get to know that how we are saying that. Okay. Okay, so this will be your model. Okay, like if you will see here, so this one is a longitudinal driver block. This one is a multi-port input block. Okay, because we are using 1, 2, and 3 cycles, and at a time I can run only one cycle. So here is one constant block is a test. So that constant block, if you will write one here, so it will select first duty cycle. If you will write second here, it will select second duty cycle. If you will write third here, so it will take the third input from the multiple input ports. Okay, fine. So in this longitudinal driver blocks, you have two inputs like velocity reference and feedback velocity. So velocity reference means whatever the driving cycle you are using, that driving cycle. Okay, I think, okay, I'm sharing my screen actually. Just a minute. Yes. So now this is clear, I think. Okay, let me check once everything is fine or not. Okay, so in this model, if you will see here, so this one is a multi-port input port. Okay, so to select any of the duty cycle just by giving the constant value 1, 2, 3. So there are three ports. You can take any of the value here, like one as or two or three. So it will select accordingly. So this one is the longitudinal block. This is representing the driver block. Okay, this is representing the driver inputs basically. Okay, so what are the inputs means you are giving, that is called a velocity reference and velocity feedback. So velocity reference is nothing but the driving cycle. So whatever the driving cycle you are giving, that is called as a velocity reference. Here one gradient is showing. Okay, one gradient is given, so there we are taking as a 0 because we are not considering that this vehicle is going in a hilly areas where some ramp is there. So that is why for the similar study, means simpler study, we are taking it as a 0. Now we are having one H bridge. Okay, we are having this H bridge, and that H bridge is controlling the motor. Means motor direction that we can control by this H bridge. What is this H bridge? So this H bridge is basically it can rotate the motor in the forward direction, in the reverse direction, and the we can say that it can stop the motor also, and we can provide the regenerative braking as well. And this edge bridge is controlled by the PWM technique. Okay, so if you will change the PWM, means if you will change the width, so the voltage, or we can say that the whatever the parameter we want to control in the edge bridge, so that will also control. Okay, But the thing is here, if you will see, one current control source is here, one current control source is here. So why we have used these current source? Because this longitudinal driver block is given output as a physical signal, or we can say that as a physical quantity. So that physical quantity cannot sense by the motor. Okay, because motor input is electrical. So just to change that mechanical input to the electrical input, we are changing this by using this controlled current source. So whatever the, see, when the acceleration is high, we can correlate these two. When the acceleration high, that means that will be a higher current. So okay, so in that way we can correlate. So what we are doing in that, we are taking this acceleration and we are connecting to this control PWM, and we are taking this deceleration and we are connecting to the H bridge. Here one block is input parameter is mentioned, which is called BRK, that is brake. Okay, and that as bridge is connected to the DC motor. So there in DC motor they have given one mechanical port, which is it is showing in a green. That port will go inside the vehicle body. Okay, so this will be the vehicle body part. Inside this vehicle body part, everything is there, like I will show this model. Now moving forward, so this above mentioned Tata Nexon EV is modeled in Simulink. Okay, so the specification of Tata Nexon EV, okay, claimed as on the test condition, that is these are the parameters specification of the vehicle, which is having the dimensions and weight of the vehicle. Okay, and whatever the electric drivetrain it is using, so the all parameters you can get online. There's no issue, like battery pack capacity you can get. Okay, what is the electric motor torque you want, and what will be the motor torque power. Okay, so that we can use. Okay, and here we are also need this wheels and tire specification. So here we have used this tire radiation, this tire size also, and I will tell you that how to convert this tire size and how to find the radius. Okay. See, so this one is the detailed specification of Tata Nexon. Like here, everything is mentioned. Like if you will see the battery, transmission, chassis body, suspension system, steering, brakes, range, everything is mentioned. Okay, so you can easily get the idea about this. Okay, and according to that only we are going to model this. Fine. Okay. So yes. So what is the drive cycle? Drive cycle is nothing, just a series of data points representing the speed of a vehicle versus time. Okay, so velocity versus time graph is just called as a drive cycle of that vehicle. Okay, here we are using three drive cycle, that one is NEDC and the second one is WLTP, which is called class 3 driving cycle. Okay, and we are using IDC, Indian driving cycle. So we will see the performance characteristic of each and every case. That one at instance we will see that NEDC, after that WLTP, and after that IDC. We will see all the parameters. Okay, we can see there is no necessity to take all the driving cycle, or there is no even we can say that we can just take only one driving cycle for which we want to see the analysis. See, if I want to see the driving performance of that vehicle with respect to the Indian driving cycle, so I will take the Indian driving cycle only. There is no need to take some other cycles also. Okay, but for the comparative study, I have taken three cycles to make sure these things. Okay, now see here, so this one is NEDC cycle. Okay, and it is running up to 1200 second. Okay, so here it is mentioned means the distance covered by this. Okay, NEDC, and this is the duration of that cycle 1180. Okay, and this one is the top speed in NEDC, if you will see here. Okay, so in that way we can understand. Okay, so this one is an Indian driving cycle which you can create by own also. Okay, so how to create this? You just type the data, means in Google you just type the Indian driving cycles. You will get some of the, or you can download the data from ARAI site. So you will get the speed versus time. You just come to the Matlab workspace, or you just create one Excel file, import that Excel file into Matlab. So it will come here, and after that you can utilize. Okay. Okay. So in vehicle body, what parameters you have to calculate, which is called as a rolling resistance, you have to calculate. Okay, like this one you have to calculate, and this one is a aerodynamic drag force. This one you have to calculate, and this one is a hill climbing force. This one you have to calculate. These three parameters is very important, which is important to calculate in tractive force. Okay, so how much tractive force you want, that is the summation of all the forces acting on the vehicle body. Okay, now see here, it is mentioned wheel radius calculation, how to read a tire. If some specification is written like this, so first section is showing is width. This R is a radial construction, 60 is aspect ratio, and rim, this one is a rim diameter, 14th. Okay, and the service description 82H, something like that. So total wheel diameter you can calculate by rim diameter plus 2 into height of sidewalls. Height of sidewalls. Okay, and according to that only you can also calculate the gear ratio. What will be the gear ratio for particular speed? Okay, so that you can find. So what will be the required wheel torque that you can calculate by at the required is equal to total force acting on the body and radius of the wheel and the width of the wheel, so that you can achieve. So these are the wheel dimensions. Okay, in this Tata Nexon case, so you can say that the aspect ratio is 60%, section width is 215, rim dia is 0.40. These parameters we will utilize in our MATLAB model. Okay, so you just have to find all the parameters. Like here I have calculated everything. So you can easily, you can just utilize, means you can calculate all these parameters by using some of the formulas, which is very means simple formulas. Like this one is a rolling resistance formula, gradient resistance, aerodynamic, and the total this. Okay, so this will give you the calculation every parameter. Okay. In this case, I have already calculated, so I will use the direct these form, how to say these numericals, this numeric value. Okay, so this one is a vehicle body. Okay, this one NR is an input parameter, whether it is this is called as a rear wheel. This one is a front wheel. This one H is a mechanical port. This W is representing here, here, just like that, the wind velocity. Okay, and this beta is representing as a turning radius. So we will see. Okay, so these are the vehicle parameters, vehicle body parameters we have taken into account, and we have filled all these things after calculation. Okay, and this one is a simple gear system, and in this gear system we have calculated, and the calculated value is 5.49, so that we will take into account. Okay, so this one is a inertia block that we have to use because some of the inertia will be there, rotational inertia. To represent that, we have to provide this. Okay, so we will see. And this one is a tire block. We can directly use tire block. Okay, just by tapping. So you just fill all the details here. Okay, like tire nominal, vertical loads, and these some of the parameters you can. Okay, so this one is the vehicle subsystem. So what I told, this one is a vehicle body. It is representing the vehicle body. This part is representing the we can say that axle of that powertrain. So you are taking the front wheel drive or you are taking the rear wheel drive. that you can check wherever this gearbox is connected. So that will be your that will be your drive system. So in this, if you will see, this um, gear system is directly connected to the rear wheel. So that we can say that this Tata Nexon EV is rear wheel drive electric vehicle. Fine. Okay. So how we will find the motor power? So the motor power is equal to the total power divided by efficiency of the transmission. Okay. If we are taking the efficiency as 95%, so that we can take that. Okay. So these are the motor speed calculation for that particular speed of the motor, and some other parameters we have assigned here. After the calculation, you can also calculate these things. Okay. And yes, so this one is a hatch bridge actually to control the motor. Okay, so the input parameter is PWM. This one is a reverse REV. It is representing reverse. Okay, and this is as a reference, and this one is representing as a brake. Okay, so these are the parameters which we have to means whatever the output voltage coming from the H bridge will be the input voltage for the motor. So whatever the voltage you are applying here, that should be equal to the motor input voltage. Okay. So this one is a PWM techniques, and so it is taking the reference. So if the reference value is means high, so it will take as 1. If the reference value is low, so it will take as a 0. So when it is 0, so it will take the reference value. When it is 1, means when it is 1, so it will take the reference value. And according to that, it will adjust the duty cycle and it will adjust the voltage. Okay, fine. Okay, so these things, they are interconnected to each other, and this one is a longitudinal driver block. Now we will see on MATLAB that how to do these things. Okay, fine. So this one is a simplified block. Means we can say that the simulation model that I have created here. So this one is a driver, longitudinal driver, then motor controller, then motor, then vehicle body, and from this motor controller and the motor controller and this motor, the battery is connected. So this battery is discharging according to that only. Okay, so we will see. So I will just create this similar model in MATLAB. You can follow me one by one so that we can you know create this model. Okay, so go to this new. Okay, so this untitled window will come. Then I want drive cycle, so I will take drive cycle source. Fine. In this case, I am taking one driving cycle. Okay, so drive cycle. Now this one will be uh, longitudinal driver. So this block will come. Okay, then I need control PWM. Always make sure that whatever you are typing is correct or not. If it is not correct, you cannot get the block also. Double click on the screen and type H bridge. Spellings will be correct. Then only you will get. Okay, fine. What else I want? I want DC motor. So I will type DC motor. So this will be your DC motor. Okay. Okay. Now what else I want? I want to design this vehicle body. Correct? So for this vehicle body, what you can do that, okay, you just do one thing, you just type here vehicle, vehicle, yes, vehicle body. So this one will come, Okay, I'm just scrolling to right to my hand here. So this will come like that. What else I want? I want tire. So I will type tire. No, not tire. I will type as wheel in Excel. Okay, if you are getting some different block, then you should search it again. What it called? Okay, so you just type tire only. Tire. So in tire, you have to this utilize this magic formula. Okay, because this is predefined here. So we will get these things and you just do copy and paste. Copy, paste, paste, paste. So we want 4. So we will take 4 just like this. Okay. 1, 2, 3, and this is 4. What else I want? I want gear system. Gearbox. I will take gearbox. Okay, this one is not the matching the criteria. We want actually simple gear. Okay, so we will type simple gear. So this will be a simple gear. What else I want? I want inertia. Okay, so I have connected this inertia here. Okay, fine. And what else I want? I want some constant as well. So I will type PS constant. Why? Because these blocks are semi-escape blocks. So the Simulink constant will not connect. Okay. So I will just rotate this and I will also rotate this. Okay. Yes. So for some clear pictures, I'm just making it as more clear. I'm taking these tires here. Okay. So every port which is having this H is a mechanical port here. So I will rotate this to connect properly. Okay. Okay. So what I can do is I can just take you can do one thing for exchanging of port. You can click on this. Actually, this is somewhat making some problem here. Okay, no issue. We can directly connect like that only. That is not a big deal. Okay, so this one, I think the basic blocks are ready. And what else I want? I want battery also. So I will type the battery. Okay, I will take the battery here. Fine. Okay, what else I want? I want controlled current source. I want two, so I will copy and paste. One for the acceleration and one for the deceleration. I will rotate these for clarity. Okay, fine. So in that way, we are going to do that. So just connect PWM to PWM, reference to reference. Okay, and this motor to positive. This will be a negative, so this will connect to the negative. Okay, and what else will be there? Yeah, just connect these H port also because these are the mechanical ports of this tire. Connect like this. Okay. And similarly, connect these A port to A. Okay, and here also A port to A. This gear system connect here, and this inertia you can connect. Okay, I have to rotate this inertia. so that it can complete here. Okay, so it is fine now. And the thing is, this N, if you want to make it as a rear wheel drive, so I will connect this to rear, and this N is also connected to the rear wheel, so I will connect in rear wheel here also. Okay, so it will be like that. And for this, I am making it as a front wheel, so I will connecting as a front. Here also I am connected as a front. That will be like that. Okay, and what else is remaining here? S port. Okay, so this S port I'm terminating. Okay, because if you will go to the description, if you will see, so here they have mentioned this S is a physical signal output port that reports the tire slip. Okay, so here we are not considering the tire slip, so we are just we will use terminator. Okay, so you can directly use this terminator here. Okay. Okay, so this one is a Simulink terminator. That is why I told you. So write the proper name. So it will be a PS terminator. So after this PS terminator, connect this PS terminator, connect this PS terminator to everywhere where this S port is available. Okay, like this. Okay, so there are some ports. So I'm copying, copy paste. I will do copy paste, and I will connect here. Okay, again I will copy and paste. So this will, I will connect here. Okay, so I'm rotating it. Okay, then again I have to use this for this fourth tire. So I will rotate it and I will connect it. Okay, now this vehicle body is ready here. What else is remaining? Okay, so wind velocity I'm not considering, so I'm connecting is here, and the turning radius is also here. I'm taking as a constant. Okay, so okay, so okay, so this is your vehicle body. This one is your vehicle body, which is directly connected to the oh, just a minute. Okay, so this one is connected here. So you can do one thing. Okay, so be clear when you are just doing the connections, because sometimes it happens like it will give you some more problem. Okay, and connect to this to this. Now this is completed. Okay, because these are the tires, so this tire should be, these tires should be connected to this. Is there any confusion? You can make it like that, so there will be no confusion now. Okay, so this is just like that. So you have connected here. You should connect here actually. This H port, you should connect to in between of these tires. Okay, so I will connect here. Fine. So now this this vehicle body is ready, and the remaining terminals we will connect. Okay, fine. So again, what I'm doing for this motor, I have to connect inertia. Okay, so I will connect this inertia with the motor here. So now I think this one, okay, this one is actually more complex. It is looking like more complex. So I'm just moving this uh, part. Okay, fine. That okay, okay, okay. And this gear block is connected to your motor. Okay, so for the clarity, I'm making it is okay, fine, fine, fine. Okay, I will just do one more thing. For instance, I'm moving here so that I can make some good arrangements for better understanding. Otherwise, this will create some problem. Okay, I will do one thing like this. And this part, okay, select this hole and just drag. Okay, there's nothing new I'm doing, just like that. Now I think it's fine. So this connect this R port to the gear system directly. Now fine. Okay. Okay, so arrangement is not there. Okay. So there is this one is your vehicle part. This one is your motor part. And now you have to connect these things. So what you are, we are not, considering this vehicle, which is going in reverse direction. So what I am going to do that, I will connect this reverse with the reference value. Okay. And what else? Okay, I am just changing this, not current source. I am using this as a voltage source. So I will take as a controlled PWM voltage. Okay, we have taken already. So we will take consider as a controlled voltage source. I think controlled. Yes, so this one you have to use. No, but this one is from Simulink. I cannot use this. I want Simscape. So again, I have to search, or it's better to go in library so that I will get all the blocks controlled. What is that? Controlled voltage source. Okay, so I want this. Okay, so whenever you are not getting in direct search, you should follow this method. Come to your untitled window and this one added here. So just copy and paste and take it out here. Just rotate these two. Okay, I'm rotating. Now what you will do, just connect this to brake. Okay, and this just connect to this reference voltage. Fine. Now what about this negative? You just make it short here, and this information you should connect to the, okay, it will not connect directly, so we have to use the PS Simulink block, PS Simulink converter. Okay, so okay, so I just want two, so I will make copy paste. Oh, It is taking the previous copy. Now fine. So I will just connect one PS block here. Okay, this is a small block, so it might be problematic to connect, but always try to connect in a proper way with, especially with this PS. This is very irritating block actually. Uh, Sometimes it's just like that only. Okay, I'm just I will do one more thing. There's one option which is which we can use actually. We just increase the size of this PS Simulink block, so that will be very helpful. Okay, now at least you can easily. Okay, so now I will copy. Okay, and I will connect here. Now this I can connect. Just some problem is happening. I have to make some space here. Okay, first I will connect, then I will arrange. Now it is showing some connection, but it's better to connect like this. Okay, it's a PS Simulink block. No, I don't want PS Simulink block. I want Simulink PS block. Simulink PS block. It's opposite because the Simulink signal is coming and I want to connect this to SimEscape. So now fine. That problem was, that is why it is was giving continuously error. Okay, and no issue. Again, I will type here Simulink PS converter and connect to one block here, and that is not connected to here. This should connect through this acceleration. Okay, and this should connect through this deacceleration. Now fine. Okay, and what else is remaining here? Okay, so you do one thing. You just take this reference voltage also, you make it short here and connect one ground, especially because wherever you are using this electrical system, you should have to connect this ground. Yes, this also I think this one is Simscape or Simling block. Yes, this is making some problem. So this problem basically happens when you are using this Matlab. So you have to see that with so that will be better option. You type here ground. Yes, here is okay. Come to the it is and just connect your ground here. Okay. So I think this part is also completed. And now the remain part is battery. Okay, fine. I have to give the reference velocity. I will give the driving cycle source. And what else I want? I want one current source. Okay. Then I will type controlled current source. Okay, so I will take it as current sources. Okay, then I will take this, I will connect here, and this I will connect here. Fine, just like that. Take copy from here only because we want one ground. I will connect ground here. Okay, so we connect ground here. After connecting this ground, so this one is our battery part. So whatever the means, one more thing I want actually. Okay, I will just move forward here. Okay, so I will connect one ammeter here actually. Okay, because I want current from this battery. So I will just double. Okay, my system is I think hanged. Okay, this one is a, we say as a current sensor. Okay, this one is a current sensor. This I want to connect. So I will connect this positive to this positive, and this I will connect directly to the motor. And whatever the remaining port is there, so I will connect through this battery. Okay, now the battery is connected. Okay, so fine. What else is remaining? So the part which is remaining is, okay, let me make it more correct so that you can understand in better way. Okay, I think this one is fine now. So what else is remaining? Yeah, feedback is remaining. Okay, so from where we will take the feedback? So we will take the feedback from this vehicle body. So we will take this feedback. We will take this feedback and we will connect directly here. Okay, fine, fine. That I have to use this PS Simulink block because I am just converting the signal. So I think, okay, now you can connect that here. So it is connected here. Okay, it's not looking good actually. Okay, no issue. And I'm taking here. So fine. So that will be your feedback velocity. Now what I told, if your feedback velocity and the reference velocity is matching, then you can directly say this is the proper modeling. Okay, so okay, so I'm taking a scope here. Okay, and in that scope I will double tap, I will go to the layout and I will select here two inputs. Okay, so there will be two inputs. You just connect one input from the reference velocity you want, and the second input you want as a feedback velocity. So connect. Okay, I need one. Okay. I have to do one more thing because fine. What I'm doing actually, I will tell you first. Yeah, I'm just taking this swimming block here so that now I can connect this scope directly here. Otherwise, I have to use again one PS Simulink model. Okay, so I think you can understand this. Okay, and one more thing, I have to give one gain. Okay, this gain I have to add in reference velocity for the conversion purpose. Okay, and let me show you once. Just for instance, I'm making here and I'm disconnecting here because I want one gain. So I will want add one gain block. Okay, and I will rotate this. I will take that gain somewhere in between. I will connect here just like that. Okay, and the same thing I will do. I will do the same thing and I will connect to the V reference. Now fine. The same thing I will do with this scope. I want one gain here also. Copy paste and I will rotate this. Okay, and I will add this. Okay, so these two things importance that I need. Okay, I will I will see the values later. What are the values? Okay, but after that you should understand this also. So if this one is your vehicle speed, okay, so this vehicle speed you want to convert in distance. So if you will integrate this vehicle speed, then you will get this distance. So what I will use, I will use one integrator. And this integrator I will connect with the speed. Okay, and I will use one summation block. You can say that. Okay, it's not. Okay, so I will use one divide block actually. So yes, where is divide? Some problem with this Matlab. Okay, fine. So I will use this divide block and what I will do. So whatever the velocity will come, it will integrate and I'm dividing by this. What I will take it as a constant block. You also take one constant block here and connect this constant block to divide. Why? Just for the conversion purpose. So I am dividing it as a 3600. Okay. So this one is for the connect. And now I will connect here one display. So I will connect here. Okay. Now this part is complete. Now for the battery SOC estimation, for the battery purposes, battery SOC estimation, I have to make some arrangement that I'm going to do that. So first I will select one PS Simulink block. Okay, not Simulink PS. Simulink PS. Okay, so I will connect this Simulink PS block here with this block. Okay, fine. This is not connecting. So what I want here, Okay, so I'm converting from Simscape to Simulink. So that is what I want is PS Simulink. Okay, now this will connect here. So always remember this, that from where to where you are doing connections, it should be very important. Okay, so okay, so I'm just using one simple method for the SOC estimation, and I'm taking it as one integrator I will use here. Okay, and then after that I will use one gain. Just be careful here. And after that I will use one summation block. Okay, fine. So I will just arrange this integrator here, connect this integrator. I will connect the gain with this integrator. Okay, and I will just change the symbol of that. So I want plus and minus. So I will just take minus. I think this one is minus itself. Okay, and yes, so I will just make sure that it is here only. I can rotate this also, so I will rotate this. That will be better. Okay, fine. And I will connect this gain to this here. And here I will connect one constant block. Okay, and that constant block I will add here. And what else? Now I can estimate my SOC. So I will just connect the not SOC, the scope and one display. So I will just copy paste here. Okay, it will tell me the SOC as well as it will give me the numeric value of this. So now this whole model is completed. Now the thing, okay. Now the thing is we have to give the parameters. So for instance, I'm taking the cycle not FETP, FTPS. Okay, you can take any of the driving cycle. So okay, like for instance, I'm considering this WOT. Okay, and I'm just applying here. For the longitudinal driver, there's no input provided, so we will leave like that. Okay, oh yeah, gradient, sorry, gradient, I have to take this as a constant value. I will connect this gradient here, and this will be like 0. Fine. Okay, now just fill all the data. So come to this EWM. Okay, here you have to fill some of the data. So that data I'm telling you what to fill here. Okay, and so here the frequency, just take 4000 hertz. Okay, and okay, and these things you remain same, and fine here. Okay, and this will be like input voltage for 0 duty cycle is 0, and I'm taking here as a 1, so it will be like 0 and 1. So what will be the output voltage of the amplitude? Output voltage I am taking amplitude as a 5 volt. That means that will supply the power to the bridge. Okay. Here I am taking simulation mode as a average. So other parameters will you should not bother about it. Okay, so this one is done. Fine. So now come to the next point, which is H bridge. In H bridge, you have to be very careful about these parameters because you are going to do that for this motor calculation, means motor controlling. So here the power supply is internal. Okay, the simulation mode, whatever we have taken in the PWM. So I'm taking here average. Okay, so it is saying the regenerative braking. So it is asking about the regenerative braking. So you just make it always enabled. Okay. And the load current I want is smooth, fine. And some of the threshold value, okay, which is 2.5. And whatever the output it is coming from the PWM, that will be your PWM signal amplitude 5 volts we have taken. And these things I'm making just like that only. And if I'm talking about the bridge parameter, so what will be the output voltage of the bridge parameter? In this case, the motor voltage is 310. So I'm taking the output voltage as a H bridge. Our output voltage is 310 and rest I'm keeping the same. Okay, so this is done. Now I will come to this. Okay, so for the motor part, as I told you, so whatever the input voltage you are having that you can enter. So there will be no thermal port we are considering. This one is a permanent magnet motor and we are just want motor pull parameters by the rated load and rated speed condition. So this will give you like this. So here, so whatever the no load speed we have calculated that is 10,000 RPM. Okay, and the rated speed which is mentioned in the motor specification is 3796. Okay, and the rated load, mechanical load, that is 84 kilowatt. If you will go through this Tata Nexon, so you will get to know, and you change the unit here, so it will be a kilowatt. Okay, be careful with the units. And rated DC water supply is 320. Okay, why? Because it is somewhat more than this. Okay, and here some mechanical parameters are also there. That is similar. That is there's no change. Some faults and okay, so faults we are not considering, so I'm taking it as a. Now I will come to the gear ratio. So I told you that how to calculate the gear ratio. Okay, so that I told you. So you come to the gear ratio and just input all the gear ratio parameter like floor to base is it is coming 6. So I'm adding 6. Meshing losses I will not consider. Blackless I will not consider. Viscous losses I'm not consider. Okay, so these things will remain same. Okay, I will check one inertia also whether it is fine or not. Okay, because this inertia is representing the vehicle mass inertia, so this is very important parameter whether we are considering or not. So if you are going through this inertia, then be sure always. Okay, okay, let me check once. Okay. Okay, so this will not be the energy actually. This will be your mechanical rotational reference. Just like that we use for the temperature, environment temperature as a reference temperature. Okay, so this will be like this. So there will be no value to fill. Now the gear ratio I have filled and the remaining part I am just connecting these things. Okay, so for this inertia, so Okay, so this inertia we have connected here, so there's nothing to change. Now come to the tire. So if I'm talking about the tire, so there are some parameters. Okay, there you should very precise, otherwise this model will not work. Come to the setting. So I'm taking it as a long, some parameters dependency will be there. So I'm taking it as a load dependence magic formula coefficient. Okay, here it will come. So I will just calculate it, the nominal vertical load, which is called like 3500 Newton. This will be same, and the rest parameter will be same. Why? Because this is already calculated by this by default. Okay, now come to the geometry. This one is important. Geometry is zero point 0.3. Okay, fine, 0.3 meter. I have to see once with my model. If anywhere I missed some parameters, you can match. There is no issue. Okay, so okay, so what are the dynamics for this wheel? I'm just checking. So there will be like okay. So inertia I'm taking into account. So fine. So this will be your inertia. What will be the rolling resistance that we have calculated actually? So we will take into account these rolling resistance. If you will on, so it will ask you the value. Now type here the value. So the calculated value is 0.022. Okay, and the velocity threshold is, it is already defined, so I will not change this. Velocity threshold will be the same. Okay, so for every tire, okay, correct. So I have to check each and every tire. Okay, I have to check this each and every tire. So I will just check again and again, and I will change the parameters just like that we have done. Okay, so it was like 3500. Okay, geometry is no change. Rolling resistance, this one is on. So just change this to, okay, what was the value? 0.022. Correct? Okay, so okay, so this one is done, I think. Okay, this one is done. Now for the this again I have to check whether all these things are correct or not. Okay. Okay, we have taken into account peak longitudinal. Okay, again here, just change this to long dependent and make it as 3500. Okay, and come to down here, specify inertia, and the thing here, just again, just do the same thing for each and every tire. Come to here and the type 0.022. I think this one is correct. For the this tire I missed, I think. Yes. So yes, here I have missed. Okay, okay. Now this one is correct. This one is also correct. The rest one tire is remaining, so I'm just doing for this also. I will do the same thing. I will make it as 3500. Okay, and here I will take it as inertia. Okay, and the rolling resistance is off, so I will make it on. It will ask for the value. I will just write this 0.22, I think is correct. Yeah, 0.022. Fine. Now come to the vehicle body part. So come to the vehicle body part. So for the vehicle body part, okay, the vehicle weight is 1470 kilograms. Okay, number of wheels per axle, two. Two wheels in front axle, two wheels in rear axle. Okay, so horizontal distance 1.4, these things are remaining same. Gravitational force is same of. Okay, now we have to make sure that drag coefficient is okay. So the frontal area we have calculated, which is 2.91. Okay, and the drag coefficient we have calculated is as 0.15, and the air density is here, it is somewhat like 1.225, which is off. Okay, initial target we are not taking into account. Nominal voltage, nothing we are taking into account. Okay, so this one is correct. Okay, and what is this PS? I'm taking it as 0. I will write here 0, and this one is also, I'm taking 0 here. Fine. And these gains are for the conversion, so I'm taking here 3.6. Okay, yes, so I will take 3.6 here and 3.6 here. Okay, now everything is fine till here. So the remaining thing is, now I want to give the battery inputs. So I will go to the battery and I will change the parameters of the battery. Like my nominal voltage is, what is my nominal voltage? Which is 320. Okay, and internal resistance of the battery I'm reducing here because it's too high, 0.02. Battery capacity, charge capacity is not infinite, you make it just finite. Okay, so what is the cell capacity for this Tata Nexon? This is 94 R ampere. Okay, and the voltage when it is charging, which is somewhat less than the nominal voltage of the motor, 300. Okay, and this one will be a minimum level of 10. Okay, it is just representing the SOC level that initially it was 94 and now it is 10. Okay, so dynamics, no dynamics, we have considered no dynamics, and fade, no, everything you should make disable only. Okay, everything will be similar, same. Now this. Okay, so I have to mention this gain. So this one is SOC estimation. So here I'm just writing the gain value, which will convert this R, which will convert this SOC in seconds. Okay, so what it will be, 1 divided by, okay, So I think everything is fine now. And one more important thing is missing here. What is that? What is that? A solver is not there. So I have to make one solver. Okay. Now I will connect this solver. Yeah. Okay. Anywhere you can connect the solver. You can connect the solver. Okay. I will just run this model and I will see that. So if you want to see the driving cycle, you just go here and plot. It will show you the driving cycle. Okay. And okay, fine. I'm taking one standard driving cycle, which is FTP75. Okay. That is that will give you a proper, see, this one is your okay. So okay. Okay, so they have mentioned here 2474 seconds. So I have to stop this for 2474. Now I will run and I will see. Okay, some errors are there, which is okay, fine. So we will rectify this and we'll see, because it happens sometimes when we do, and some of the blocks we missed by default. Okay, so it happens actually. So I will resolve this and definitely. Okay, so okay, so after the means some of the corrections, and I made some of the changes here. So if you will see here, so actually some connections problem was there here itself. Okay, so you just have to follow the connections scenario. That is what I told you. Okay, if you will miss one of the connection, and you will get error. Okay, so that was the problem here, some of the problems. So that is why I made some of the common blocks here, so for the better understanding that where we can have the problem. Okay, so everything is fine, rest this thing. And I have also connected, this one is called as a multi-port switch. So you just type here as a multi-port switch. Okay, so you can connect like this. And here I have connected one NEDC cycle. This one is a different one cycle, and this one is a WLTP cycle. Okay, so we will see one by one. Okay, so for, if I want to check for NEDC, so I will type here 1. It will take the NEDC cycle. Okay, so before that I have to check the NEDC cycle. Okay, so I have to, okay, so for this NEDC cycle, I'm running. Okay, it's run, and now I will check with this as the scope which I have connected to check the reference velocity to the feedback velocity. If I'll check here, so it is following the reference velocity. If you will see here, the yellow one is a reference velocity and the blue one is a vehicle speed. So it is similar to, it is following the graph. So that means this vehicle powertrain is whatever we have designed is correct only. Okay. And if I'm talking about the SOC, and if you want to see the SOC level, so this one will be the current drawn from the battery. Okay, which is representing a particular segment of the driving cycle. And if you will come to the SOC level, so this one is your SOC level, which is coming down here. Okay, and just a minute, I will expand this. So if you will see here, this SOC is coming 1 to almost we can say that 0.88. Okay, so 100 to 88% it is coming down. Okay, so for this I am zooming out to see the distance. Okay, okay, so to see the distance, I'm zooming out. So the distance covered by this vehicle is 1.594 meter. Okay, or okay, some other parameter also. If you want to check, you can check at any point of instant. If you want to check, you can check. Okay, so the current, the SOC of the battery, and the distance covered by the vehicle, we can directly take it into account. Okay, see if I will change here to Indian driving cycle, so I will just type this too, and I will run this, and we will see that what will be the SOC. Okay, so in this time, in this case, it is covering 2.047 kilometers. And if I will show you the reference velocity, so it is also following the same pattern, which is we are taking into account. Okay, and this one is your current run from the battery. Okay, and if I am talking about this SOC, so this SOC is coming down from 1 to almost means less than the previous one. Okay, so just like that we can compare. Okay, if I'm tapping here for the third, because we have taken 3 cycles, so if I'm taking here third and I'm applying and I want to check, then I can do that. Okay, so again, first thing is check this one. Yeah, it is correct only. So if it is coming fine, then that means your model is running fine. Now check the current. So this one will be your current characteristic for the different cycle, and the distance covered by this we can say that the driving cycle by 1.878 kilometers. Okay, and what will be the SOC level? The SOC level will be the similar to the first one. Okay. So these, I think this one is clear to all of you. And I just want to tell you the conclusion of this whole project. Okay. So yeah. So, okay, I will show you one by one. So these are the results of this. So for the NEDC cycle, if you will see the SOC, so this will be your SOC. Okay, and this one will be your reference and output voltage speed, and this one will be your current. So that is what I have shown you. This one is a IDC cycle. For the IDC cycle, this one will be your SOC, just coming same 0.86 around, and this one will be your reference speed. This one will be your current profile. Okay, I have mentioned here time period also. Okay, if you will see for each and every case, I have mentioned 812 seconds. Okay, and the first cycle is for 1180 seconds. The second cycle is for 812 seconds. The third cycle is for 1800 seconds. So whenever you will type the time, stop time, you just write these times, note down these points. Okay, so what we can conclude it. So the conclusion is just like that. We have these driving cycle. So if you will see the in Indian driving cycle or this the SOC is going very deep, means the battery is taking more consumption. Battery is discharging more with Indian driving cycle because of the retardation and the start-stop operations are very means most prominent things in Indian driving cycle. So because of the driving is means we can say that because of the driving situation here, so that is why the SOC is very high. It's 85.55. It is coming down from 100 to 85.55. If you will talk about this WLTP, so in this you just we can say that the SOC level is coming to 66.15. Okay, so it is going very deep, like we can say that, and the distance covered by this vehicle is 6.64. So in different scenario we can analyze a vehicle performance. So that is the conclusion for that, and what we have actually learned from this project is that it is possible to operate a vehicle beyond a mentioned peak speed. Okay, that means we have concluded that by just this we have concluded, if you will just read this NEDC, so here the top reached is already meet. Okay, so okay, so this one thing, and the drive ratio are dependent on the drive cycle definitely, and the SOC through the dependent driving patterns that we have seen. If in a drive cycle at multiple times the vehicle is operated at an intermittent zone of motor operation, the SOC falls drastically. Motor sizing and calculation we have seen. So many parameters we have included, and we have calculated here, and we have seen the characteristic of that. I hope this project will help you, and definitely you just try to simulate this. And thank you very much.